So okay, any questions before I start? So everyone's okay with the assignment for Thursday? Okay, good. So today the goal is to understand something a little bit different. It is to understand this idea of photometry versus radiometry. So everything we have talked about so far has been dealing with SI units and so on. So we talked about watts per meter squared and joules per second and all this stuff. But in many lighting applications, we need to think about the human perception. So in other words, when you try to design the headlight of an automobile or the lighting inside a room, whoever's doing daylighting, you need to not think about watts per meter squared, but also need to consider how the human eye responds to light. Which means that we need to think of, there's a slightly different units that you need to think about because it takes into account the spectral responsivity of the eye. And this field is referred to as photometry in general. Okay, and we'll also talk briefly about color, which is very interesting as well. Okay, so the first we need to define quantities and have a common language to talk about these things. That's the first goal here. So we'll start with the simplest things, power. Okay? Power, as we know, is nothing but flux, right? Photons passing through, and each photon carries some energy, and how many photons are passing through per unit time, that gives us flux. Okay, it's like current, for those of you who are doing electrical engineering, right? So we can think about this as radiation flux. It's terrible. The radiation flux, so it is the quantity of energy that's emitted, transmitted, or received per unit time. So this means, of course, it depends on what you're thinking about. If you're talking about a solar panel, for instance, it's what energy is received per unit time. If you're talking about a source like the sun, how much energy is emitted, and if you're talking about, let's say, a window, how much energy is transmitted. So it depends on the situation, but it's all the same quantity. Okay, this is flux, and it's defined essentially as the rate of change of energy. Okay, just like everything else. So this is radiant, it's not photometric yet. So we'll start with something very familiar to us. Radiant flux is the same as radiant powers in terms of watts. Okay. Now, the difference when we talk about human perception is the fact that we, as human beings, see only those colors, which is a small sliver of the entire electromagnetic spectrum. And we also see this in a very specific manner with the sensitivity, which is shown here in the blue curve. So that's relative sensitivity of our human eye as a function of wavelength. So you can clearly see peaks around 560, something like that. Yeah, which is in the green, which is primarily because that's where the most photons coming from the sun are during the day. So we evolved to essentially see very well here. And you can see at the tails, but we have a pretty long broad spectrum, goes from the blue all the way to the red. And it depends on the person, right? This is an average, so some people can see, for instance, into the infrared, what this part called near infrared, whereas some people can't see, and it changes with age and so on. Younger people can see better in the blues, for instance, whereas older people tend to see less in the blue. So it depends on, but we have to have standards in order to design this. So this is a standard curve that people use, and it's referred to as the photopic luminous efficiency function. We'll talk about it briefly. Now, from the point of view of this class, of course, I don't need you to memorize any of the stuff. Conceptually, I want you to understand what we're talking about. That's the most important thing. Okay, so luminous flux. So in the previous slide, we talked about radiant flux, which is the power in watts. Okay, luminous flux is when you take that power and try to superimpose the human perception. That's the only difference. So radiometry talks about absolute values. Photometry simply applies human perception to those absolute values. Okay, and they're analogs. Every quantity here is an analog here as well. We'll talk about that. So the human eye has different sensitivities at different wavelengths. This is described approximately with the luminous efficacy function. And luminous flux is the perceived power of light by the human eye. And the units are different. Okay, we talk about, these are called lumens. And you might think this is kind of outdated, but it's not, because if you, for instance, go try to buy an LCD monitor for your TV or computer or something, they're always still spec'd in lumens or more modern units are called nits. So you can actually go and see it. This is a very important field. We will touch briefly about it in this lecture. Okay, so the luminous or the efficiency function of the spectral sensitivity of the eye is also called the luminosity function or the photopic luminous efficiency function. Of course, you don't need to memorize any of these names. It's just the spectral sensitivity of the eye. Okay, and we saw that. So in general, it has a unit, right? But the efficiency is translating from. You have some markers? Did you bring your markers? So the efficiency is translating from radiometric to photometric units. And this is too dark. Hopefully you can see it. Photometric to radiometric to photometric units. So watts to lumens. So the transfer is from watts to lumens. So you have some equation which lets you transfer from watts to lumens, which is in units of lumens per watt. Okay. So that's. So you have lumens here, and you have watts here, and you have something that allows you to go back and forth, right? And it's normal. It's a normalized function, and the number 683 is just the normalized integral of the sensitivity function. Not important for us, but just be aware that the spectral intensity of the source, or spectral irradiance that we talked about before, is the V of lambda. That's in watts per nanometer, right? That's the source spectrum, like the sun spectrum. Now, if you multiply it by that number, 683, it just gives you the normalized, what's called the photopic efficiency, or how your eye perceives. Again, not terribly important for you to, I would say, I think it's more important just to appreciate that there is this analog between these two. So in general, these depend on the light level. Just keep this in mind. For instance, if you're designing something for night driving, like we talked about in one of the previous lectures, you might want to design it for what's called the photopic response, which is the low light response right here. Okay. Or you can have what's called the photopic is the well lit conditions, so it's shifted to the red. Whereas the mesopic and the scotopic is the low light conditions, which is a little bit shifted to the blue. So if you remember, we talked about lighting in the parking lot or driving, what kind of color is better, right? So if the peripheral vision is more sensitive of blue light, so if you have bluish headlights, for instance, that might be sometimes better in some cases. Well, actually, we didn't talk about it. So this is the example I wanted to actually show. For some reason, I talked about it. Let me just turn off the light. So this is a good example of where this becomes important. So in this, there are two situations here. Which street lighting is better for driving? The high pressure sodium lamps on the left, or the metal halide lamps on the right? So right mentioned the metal halide lamps. And I assume it's because you're saying because you've got a peripheral vision in the middle, right?
Based on the last graph.
Yes, so is that clear to everyone? So we don't need to discuss it too much, but the fact that under low light conditions you get more sensitivity in the blue means that you may want to have more bluish light for nighttime vision as opposed to more reddish light. Okay. It's a very, very simple example of why we need to know these things, right? Obviously, there are more complicated things that you take into account to do these things. Okay, so moving on. In general, of course, any source doesn't just emit in one wavelength. You get a whole range of wavelengths, which means that you need to do this integral. So if a source emits more than one wavelength, then the strength of the total visual sensation is the integral over all the wavelengths. So in that case, phi of lambda on the right-hand side is the source spectrum, which is in watts per unit wavelength, which we have already seen. That's the standard spectrum. You do the integral multiplied by V of lambda, which is our spectral sensitivity of the eye. Okay, so this here is the source spectrum. This is the sensitivity of the eye. Multiply them together, that gives the response of the eye. You integrate it over all the wavelengths, that gives you the total response. Don't worry too much about that number. It's just a normalization factor that gives you what's called the total luminous flux, and it's in units of lumens. Whereas on this side, this is in units of watts per nanometer, let's say for wavelength, And this is in units of lumens per watts per nanometer. So they cancel out, so everything becomes actually, yeah. So V of lambda, if you recall, we saw it here, is in lumens per watt. Okay? So the watts essentially cancel out, and you end up with lumens. The 683 takes care of the per nanometer because you're doing this normalization business. So you don't have to worry about that. Okay, now we have to talk about these strange units called lumens, and there are other things which will come. So let's talk briefly about that. So what is a lumen? A lumen is a fundamental unit of luminous flux. So in other words, it is the power density. It's an analog. So lumens are watts. So radiometric analog to watts, right, as shown here. But we take into account the perception of the human eye. That's the key difference. So it is a measure of the total amount of visible light emitted by a source or received by a receiver, if you're a human, right? So typically you think about the source because you want to, let's say, design this system such that you have a certain color of light in your room, for instance, right? So you talk about the lumens of that source. Okay? This differs from power because luminous flux takes into account the wavelength sensitivity of the human eye. So in order to understand what this is, we need to start with some more basic units, something called a candela. Okay? This comes from historical reasons, but we need to know what it means. So the candela is defined as, which is a unit of what's called luminous intensity. So let's write these things down. So it's candela. It is similar to intensity, right? So intensity would be watts per meter squared. Right? So we'll come back to this later on, and we'll correct things too as we go along. So it is the unit of luminous intensity, which is the power. So let me just point this out. It is the unit of luminous intensity, power emitted by a source in a particular direction with the spectral sensitivity of the human eye taken into account. So there is one difference here than the intensity we talked about, is the direction. So it depends on the direction, which turns out to be very, very important when you're trying to design lighting systems. We'll come to in a few slides. The formal definition is the following. The candela is the luminous intensity in a given direction of a source that emits monochromatic radiation of a certain frequency. Not important, it's green light. And that has the radiant intensity in that direction of 1 over 683 watts per steradian. Now, what does that mean? So I missed one unit here, which is steradian. And we'll see what this means in a second. But steradian, let's define steradian let's review, because you're expected to know this. Let's try to think about what steradian is. It is solid angle. So steradian is the unit of solid angle. Okay? And the idea is simple. In other words, if you have a surface in space, three-dimensional surface, and you're trying to find its angle, you have to define it in 3 dimensions. Right? There's a little volume there. Right? And that unit of how you define that little volume is a steradian, so omega. Okay? And you should have seen this in high school or freshman physics or something. But there are some properties of this particular dimension, is that if you integrate across the sphere, in other words, if you do this d omega over the entire sphere, the total steradians is 4 pi. Okay. In other words, the whole thing, if it's a uniform sphere, it becomes 4 pi. Now, why is this important? Because if I'm designing a lighting system like this, it's very important where I'm looking at from. Sometimes, like I want to make sure if I want to have the different situations, if I want to have perfectly uniformly illuminated room, which is for instance what I want here, then I want to make sure I install these lights in a certain fashion such that there is very good, very low variation with steradian. In other words, if I look here or look there, I should see basically the same thing, which I don't because that's not perfect right now. Right? You can see variation. On the other hand, you might have a situation where you are in a retail store where you want your attention focused on a particular product, and you're just designing to be very narrow, right? Everything else to be, or if it's in a theater or something. everything else to be falling off, and then you have a very narrow angular dependence. And we'll talk about that briefly. So, excuse me, that's the definition of candela. So candela is basically power per area per unit solid angle, which means that I'm looking at it in a particular angle. That's it. Again, we can change with angle. That's the key. Approximately, candela is the luminous intensity of a candle, which is, of course, where the name comes from. And the lumen, as you can see, lumens should, I think it should be this. We'll come back to that. We'll correct it if I'm wrong. I don't remember these either. I have to look it up. But the relationship between the lumens and candela is that the lumens considers the total solid angle. In other words, the source is everything everywhere, and I have to collect all the rays and integrate them all. That means I have to take the candelas, multiply the steradian, whatever steradian that I'm looking at. Okay, and that gives me the lumens. That's because it's the flux. So a light source that uniformly radiates in one candela in all directions has a total luminous flux. So imagine I have a point source, say, and it's illuminating everywhere in a big sphere, like our sun, let's say. Okay, our sun's a point source, but at least imagine. And it's one candela is a source. What's the total luminous flux coming out of it? We take the one candela and multiply it by the total steradians, which is 4 pi. So it gives you 4 pi times 1, and that's about 12.57 lumens. Okay. We'll do a couple more examples. I know this is a little bit abstract because we're not used to thinking about it this way, but that's why I want you to conceptually kind of start thinking on it. It's not complicated, but it's a little bit different. So let's try to do this problem. Okay, and you can discuss. Let's take a few 30 seconds or so. What is the maximum luminous flux of an LED whose luminous intensity is 1 millicandela? It's an LED, it's a source, very standard problem. Its luminous intensity is 1 millicandela. I'll let you think about it, and you can look at the previous slides if you want, and then try to answer this. I'll let you think for 30 seconds, and then we'll try to work it out together. You can talk if you want. Okay, I'm more interested in how you approach the answer as opposed to the actual answer itself. So let's think about this together. First, luminous, so it's very similar to the previous statement there, right? Luminous intensity is 1 millicandela, which means that I have this much power going, lumens per steradian, 1 millilumens per steradian from the source, right? And I'm going to assume that it's uniform. Now, you will see later on, an LED is not uniform. But for now, we're just going to assume it's uniform. It's going everywhere. Okay. But an LED, typically, is not a point source that emits into a sphere, right? Right? Because why? Because it's planar. You need a contact, you need some material to emit the light, right? You need something. So an LED typically looks like a substrate, right? So I have one in here which actually you can see. So I'll pass it around. This is actually pretty interesting. Don't turn it on and look at it. It's very bright. But you can pass it around. You can see the LED chip in there. I brought it for another reason, but you can pass it. There's a big parabolic lens in front, so you'll see it magnified. Pretty big. So an LED looks like a chip, right? So if I take a cross section of it, it looks like this. Something, and there's some active region here, and usually I have some contacts up here, contacts down here, and so on, and some electronics and so on. And the light basically comes out. That means I have emission only in half the hemisphere. So then if the sphere total steradian is 4 pi, the hemisphere is 2 pi. Right, okay? So I have 1 millicandelas, 10 raised to minus 3, multiplied by 2 pi steradians. That's the total lumens. That's my flux. Okay? So you can pass it to the front. Okay, so it's very simple, right? Once you start thinking about it, it's relatively simple. Now, why is this important? It's important to remember because not only for lighting, for automobiles, even for the sun, if you're trying to do day lighting, but also for all displays. So your iPhone, right? You look at your phone. The way it's illuminated is by something called a backlight. Okay, and the backlight, if you actually open it up, is a little strip of LEDs on the edge here. Okay, and it's very, very, very carefully designed. You should put it down a little bit further away so you have light. Right?
No, I can see it.
Oh, you can see it.
Yeah.
So there is a strip of LEDs which are designed very, very carefully based on the luminous flux of each of those LEDs and how they're distributed and so on, because you want to make sure it's super uniform and you don't want to see hot spots and so on. It's a very important area, and a lot of people work. In fact, one of the hottest areas for jobs, if you ever go into this field, is in augmented reality and virtual reality, right? If you want to design these head-mounted displays for gaming or whatever, such that you have little displays either sitting up or on your face or something, which is very, very uniform and very high resolution and so on, right? Anyway, so I think you have an idea. So that's why we think about these, although these are really strange units. Now, what is a lux? Lux is the next unit we need to think about, which is related to irradiance or luminance or luminous emittance. There's lots of names to it. Okay, so lux is the SI unit of illuminance or luminous emittance, measuring essentially luminous flux per unit area. So it's lumens per unit area. Okay, this is equivalent to intensity. So I was right here, and let's write flux here. Remember, these are not equal; they're analogous, right? One is for photometric quantity, radiometric quantity. I just want you to kind of visualize that. Okay. So intensity is what we talk about, right? So for instance, irradiance of the sun, if you go outside today and measure, it's so like 1,000 watts per meter squared, roughly. Okay, nice sunny day like that. So that equivalent photometric quantity is lux. Unit is lux. It's referred to as lumens. So 1 lux is 1 lumens per meter squared. Simple. It's the same as 1 candela times 2 radians per meter squared. Okay, now let's do a couple of examples, very simple examples. Let's start with this. You can think about it. If we want to achieve an illuminance of 500 lux for a home kitchen, what is the minimum required luminous flux from a single fluorescent light? Let's say you're only using a single light. Okay, so you can discuss for 30 seconds. Again, these are very simple, but what I want you to gain is intuition. You can discuss. So how would I should give you 30 seconds or so. I want you to think first. Try to figure it out yourself, and you can discuss if you want. How would you address this?
I need to know the area of the kitchen and the floor.
Yes. Right. So again, conceptually, we are trying to get, let's say, 500 lux. What does that mean? That means we are trying to get a certain intensity per unit area. Let's imagine this table is our kitchen, right? The goal, again, I want you to visualize, is that if I pick any point on this table, which is the location of the kitchen, I want the intensity of light to be identical. But for a human being, not for a power meter, which is what you would do when you say intensity. But for a human being, you would say the lux must be the same, right? That's the illuminance. So if you want 500 lux and you want to get it from one source, you want to put one source here, some distance away. Of course, you have to calculate. But the question is, what's the luminous flux you want out of the source? So the way you would do it is you would take the goal here, which is the 500 lux, and divide it by the area required. Okay? Sorry, multiply the area required. So let's say the area of the kitchen is, let's say, 100 meters squared, and your goal is 500 lux. So you take 500 lux, multiply by the area, let's say 100 meters squared, 10 by 10 meters, let's say. That gives you 50,000 lumens. Right? Lumens is lux times meter squared. Lux is lumens per meter squared, right? Now that's a pretty giant, that's a lot of lumens. Right? You need maybe a fluorescent light. So the conceptual insight here is the next question. What if you want to light a soccer field? Of course, it scales with area. Right? If you want to maintain, which is common sense, if you want to maintain intensity, you need to have more flux coming from the source, obviously. Right? Which is why, for instance, this room has so many different lights. Right? Many reasons, of course, to get uniformity with a single light is very difficult because most sources are not uniformly distributed, as we will see in a few slides. So you want to use multiple sources. So, for instance, if you look at that wall behind you, it's fairly uniform. Right, except for the shadow of the projector. And they design it. It takes some design engineers, some optimization, and some careful design to actually figure out, okay, what light and where to put it and so on. And people do it for automobiles, all this kind of stuff. Okay, so moving on. We'll do a few more examples as we go along. I should speed up. Okay, so now we need to look on the other side to radiometric quantities, a few more radiometric quantities, and then we'll come back to photometric quantities. One is emittance. All of these are very similar, and we've seen this before, but so it's kind of a review. First one is emittance. It is the radiation flux emitted per unit surface area. So this is just, for instance, sun or black body or whatever, right? So M, it's defined as M, which is flux per unit area. dA is some infinitesimal area emitting radiation. It's the same. Another name is irradiance, radiation flux falling on a surface. So if you go outside and measure, that's called irradiance, watts per meter squared. Same definition. The corresponding photometric quantity is luminance. Its units are in lux. Okay, we saw that. And intensity is defined as flux per unit solid angle. So now we are defining a new unit in terms of intensity. We ignored the angle before. So the new thing is intensity, is watts per steradian. By the way, I should also point out, there's no need to memorize any of this, right? You can look it up. You just need to know where to look, obviously. So intensity is defined as flux per unit solid angle. So total flux is watts per steradian. Okay? This is very similar to what we just talked about. So the corresponding photometric quantity is what we said, is luminous intensity with units of candelas. So exactly what we talked about. So this is radiometric, watts per steradian. Photometric is candelas or lumens per steradian. Watts correspond to lumens, right? As we saw before in our table up there. So this is relatively simple. Now, let's also define the radiant intensity, which is the same as here. So this is the radiant intensity, watts per steradian. You can visualize it as shown there, which is if you have a source and you're looking at a particular angle, that particular solid angle gives you radiant intensity. So how much flux is reaching that particular surface divided by the solid angle of that, subtended by the surface in the center of the source, as you can see there. The radiance is defined as per unit area also. So there are lots of terms here. I don't want you to get confused, but just be aware, the main things to keep in mind are per unit area or per unit steradian, right? There's not too many things. So here, you can look at my little simple table here. One is with watts, okay, or lumens. Watts per meter squared, or lux. Watts per meter squared per steradian, candela. Just three things to kind of keep in mind, although there are lots of names for it. So radiance is basically similar to candelas. It's radiation flux per unit projected area per unit solid angle, watts per steradians per meter squared. And it is defined by this L, okay? It is d phi, which is, so we are looking at a surface here, and we're looking at a particular direction, okay? So that's defined by this dashed line here. That's the normal to the surface. Theta is the angle of this line direction which we are looking to the normal, okay? So then you get a dA cos theta, which is this cosine function, right? Remember, same as what we saw before. You have to project this area in the direction which we're looking, so that gives you dA cos theta. Everything else is the same. So d phi or d omega is the same as before, flux divided by steradian, divided by the projected area now, dA cos theta. Okay, so that's the radiance. Now, we can of course define a corresponding photometric quantity, which is luminance. Okay, and it looks exactly the same, except that we have a little b there because of the unit b of lambda. Remember the spectral efficiency function for the eye. So you have a visual flux on the top, everything else is the same. So now it's candelas per meter squared. Okay. Yes. So make sure candelas per steradian, lumens per steradian per meter squared. Yeah. So radiance and luminance can be functions of wavelength, so then we can define a spectral radiance and spectral luminance. In other words, you can integrate over wavelength as well, just like before. Okay? Not terribly important for us. The luminance, yeah, so it's related to spectral radiance, as I said before, just by this normalization factor, so integrate over all the wavelengths, L of lambda times V of lambda, you get the luminance. So this is the spectral radiance. V of lambda is the spectral radiance, L of lambda is the radiometric radiance, and this is the luminance, which is the photometric radiance. Okay. Now the radiation intensity is simply a unit area. So you take the emitted by an area dA is simply d phi or d omega. Okay. So intensity, as we defined a few slides ago, is watts per steradian. So it is flux here. Okay. The numerator is flux divided by steradian, which from the equation from the last slide, this slide, flux by steradian is L times dA cos theta. Right? Simple. So we get this very relatively simple expression that the intensity is now cos theta times the luminance or radiance. Now, if the radius is uniform over an area A, then you can integrate over A without worrying about how things change. Then you get I of theta, which is, for instance, what I'm trying to say is that if you look at a source here and I move around and look at it at different angles, how does that intensity change? Visual perceptual intensity change. Very important, right? That's this thing here, I of theta. And the simple expression is that it says it depends, of course, on the emittance of what is the source doing, how is it emitting, multiplied by A of cos theta. A is the area of the source. And theta is the angle at which you're looking. If you also make the assumption that the radiance is independent of the direction, in other words, the source is simply emitting everywhere equally, okay, L of theta is L, then you can simply write this whole thing as a constant. This becomes L times A. We can write this I naught. Okay, this gives us a very important law called the Lambert's law. Okay, this we will see again and again. Many surfaces are called Lambertian, or many sources are called Lambertian if they follow this law, that the intensity follows a cosine theta dependence. So if I look at a source and look at it at different angles, if its intensity falls as cosine theta, it obeys Lambert's law, and it's called the Lambertian surface. Most LEDs turn out to be Lambertian. Okay? So the key thing is that it only depends on the angle. Right? It doesn't depend upon which part of the source you look and so on. So no sources are perfectly Lambertian, only this is an ideal situation. So let's do a quick example, okay? Just to review what these things mean, which I did not draw, so let me draw it on the board. Let's think about a very practical case of an LED. Okay, you have a gallium nitride substrate. Gallium nitride is very common for an LED. You have an LED. You usually have a planarizing layer. This is silicon nitride. Okay, SiNX, let's say. It's transparent. This is just to protect the material here. And let's say you have an active layer here, which is typically gallium nitride, but it's let's say like a quantum lab. Not terribly important what it is, but let's just imagine, okay? This is our emitting region. So I'm going to make this really small for simplicity. Okay? And we have light coming out, all directions. Okay? I want you to think about, and maybe draw, what does the light coming out into air look like? So this is air, this is silicon nitride, this is gallium nitride. From the gallium nitride active region, I'm getting light in all directions. In fact, light's also going down. So I'm not going to collect it, obviously, right? Let's imagine it's going in all directions. In general, it is. But we're not going to collect what comes down here because this substrate area blocks the light and so on. People do some tricks to collect it, but let's not worry about that. Okay? Just imagine it's going everywhere. I want you to tell me what will the rays look like here, and you know how to do this today. So just, if you have a piece of paper, draw. And you can discuss if you want. So I'm trying to combine some things you've learned before. Well, I can ask questions like this for the exam. Right? It's not much math, but conceptually, you need to be able to understand what is going on. And I like questions like this. I haven't drawn anything there, so this is just a note to myself. So just think about what is going on, right? The light's coming from the nitride. And let's just simplify our world a little bit and just look here. What happens to a ray here? Can someone tell me?
It gets bent a little bit.
Right, okay, so let's just follow this ray. It hits. What happens at that interface?
Secondary wavelengths.
Sorry, refracts and what?
Secondary wavelengths. Secondary wavelengths are.
Yeah, secondary wavelengths, which lead to refraction. So Snell's law happens here, right? It goes away from the normal because the refractive index of silicon of anything is larger than air. Right? Anything goes into air, it has to go at a larger angle. So you don't even need to know what the refractive of silicon nitride is. But let's just say it is 3. It's about 3. That's it. Rule of thumb. Okay, so the angle here and the angle here has to be a little bit larger. So that's good. But what is the largest angle that will come out?
Critical angle.
Actually, before we do that, anything else that will happen here at this interface?
Reflection.
Yes, some of the energy will be partially reflected because of Fresnel reflection, right? There will be some reflection here. So only partially it will come out, some of it will reflect. And this can bounce around. We'll talk a little bit about this. This is referred to as light trapping. We'll talk about this, I think, in next lecture. A couple of lectures. Anyway. So the next question I want to know, if I'm looking from up here, what will I see? Right? This is my eye. I'm looking down at this LED. What will I see? That's the real question because this is what we're trying to do. So I will see light coming out at many angles. Right? I will see a nice big spot, let's say. But what defines the extent of that spot? Like, what is the largest angle I will see? Which is what you said, is a critical, right? So let's follow a ray here. Okay, let's say it comes at an angle slightly higher than the critical angle. What happens? You will see total internal reflection, right? So light, 100% of the light essentially reflects, and then it's trapped, unless you do something clever, which we will also talk about in this class. So let's say we're not doing anything clever, that light's gone, right? So the LED emitted in all directions, or I get out here, is a cone, which is defined by the critical angle. Sorry, actually, the cone doesn't look like that. The cone actually is 90 degrees, right? Because like that. But of course, the efficiency goes down, so you actually see a dimming on the sides. But the cone inside that can couple out. So if I were to redraw this, let's say silicon nitride, air, this is my normal. The cone, I'm going to draw a point source for simplicity. This is the cone that will make up. And that's defined by the critical angle, right? Everything outside this is trapped. It doesn't come out. So, for instance, if I know what the lumens are, I know what the critical angle is, I can compute what is the lumens. If I know what the candelas are, I can multiply by the solid angle to get the lumens that actually make it out into there. That's why I need to know this. Okay. It's a simple example. I shouldn't complicate it so much, but it's a very simple example. Yeah.
Aren't LEDs like pretty directionally independent? Because like
Yes.
if you look straight in the LED, it's super bright, but if you look
Yes.
off to the side, it's not very bright at all.
Yeah, which is my next slide.
Oh.
So, of course, no one makes an LED like this anymore because you can do more clever things, right? I can put a lens on top of it. I can shape the surface and so on, which is exactly my next slide. So that's a good question. So that's an LED is a traditional Lambertian emitter. So let's see what this slide says. This says a lot of things, and it's important for you to conceptually understand what this is saying. So the top row is showing different schematics of an LED. Okay. So A is a planar LED, which we just talked about, but almost no one ever does. Okay, there's a flat surface. That's your point source down here. Let's say that's your gallium nitride. This is your silicon nitride, right? Then you're limited like what I just said. This gives you this plot right here. Okay, this circular plot, which is what we said. It goes from 0 to 90 degrees. So this is a polar plot, by the way. The way to read this plot is this is a normalized plot here, 0 to 1. And this goes from minus 90 to 90 degrees. Okay, and this circle here just means that you are getting light in all directions. But of course, at very large angles, you're going to lose a lot of the light. Okay, most of the energy comes within that cone defined by the critical angle. Now, many LEDs do what's in the middle. You basically shape the surface on the top. It's just like putting a lens, right? Just like the one we just saw here, for instance. It can be a physical lens like this, or you can actually shape the actual substrate. And you get a hemispherical LED. And then you get this plot. Perfectly Lambertian. It's like perfectly going everywhere. Okay? Which of course is an idea as it really doesn't happen that way. Now you can see from Snell's law why this is the case, right? Does everyone see that? Let me draw this because it's important for you to appreciate. Look at the middle picture for a second. At the middle one. And let's think about what's happening. I have going to draw a circle and a point in the center. Okay, I'm going to cut it, of course, right? It's a hemisphere, but that's just a circle. If I draw any ray here, what happens to it? Straight. Nothing happens to it. Because the radius of this circle, right? This is 90 degrees. Go straight up. No there is reflection. There's a little bit of reflection, but it's zero incidence angle to the surface. Right? I can draw any ray, just go straight up. Right? Which is what that big semicircle is saying. Right? Just go straight up. Nothing happens. On the right-hand side is typically what's done. It's a parabolic LED. Okay? And what happens there is this. Good. Which means that it's very directional. Okay? And this is the example where I wanted to show this. So this is a lens. Okay? It's an aspheric lens, as you can see probably. And you can see the chip in there, right? All of you saw the chip in there. Now, I can change its focus by essentially moving in and out. Okay, and I'm going to do that and we'll see what happens. When it's at the focus, you should see a bright spot. I mean, you'll see the smallest spot, right? And yeah, I'll start with one edge. So this is when it's completely defocused. So I have to turn off the light. See this better. So it's not that dangerous. You see that nice and uniform, big. So this is like the one in the middle, right? It's not ideal, obviously, because it's a lens, not a perfect lens, right? And it's a white LED. There are chromatic aberrations. In fact, if you look at the edges, you see some red and so on, right? Those are chromatic aberrations. Now I'm going to change the focus. So I'm going to stand back a little bit. So as I change the focus, the beam's getting smaller, which means that I'm reducing the angular length. So I'm making it more directional, right? And you can see there's more chromatic aberrations and so on and so forth. And at some point, I'm going to form the image of the LED. Those are the contacts of the LED. Right? I'm forming a magnified image of the LED now, because now I've gone past the focus. So this is geometrical optics. You know how to predict this, right? And as I move back, it will defocus, right, on the screen. But I can focus it again. I just suggest, well, actually I can't because I'm at the edge. Can't move anymore, but you see the idea. So this is, of course, very important for all imaging systems. This is a very simple example, but you get the idea. So sometimes you want to collimate the light, which is where this directionality becomes very important. I'll show you some examples of that. Okay, we need to speed up a little bit. Let's do these two examples, and then we'll wrap this part of the lecture up. So I want you to do this yourself now. Okay, this is based on what we talked about today. You have a point source. A small point source emits light equally in all directions with the radiant power of 10 watts. What is its radiant intensity, and what is its irradiance at a distance r? Spend about a minute, and you can discuss if you want. You should be able to do this. At least you should know how to do this by the exam. This kind of problems, anyway. So this is identical to the picture I've drawn here, right? Yeah, point source, then I'm looking at some distance away, basically. I don't have any optics, obviously, in this case. So it's just the source. Most of the time, when I look at these problems, I get confused by the terms. So what I recommend is just become familiar with what the terms mean. And once you get that understanding, then these sorts of problems become much easier. Okay, so it might be a little complicated or abstract at the moment. But if you kind of think about it a little bit at home, I think it'll come. So in the interest of time, I want to keep going. So let's go to the solution. Okay, so it's relatively simple, right? So you have a radiant intensity, which is what? Which is the power per solar angle, right? We define intensity that way. So you take the total power, 10 watts, and you assume that it's emitting everywhere into 4 pi, divided by 4 pi, so 10 divided by 4 pi watts per radians. Now, radiance, on the other hand, is defined as power per unit area, right? So in that case, you take the 10 watts and divide it by the surface area of the sphere, which we have done before for the sun and so on. Right? So you take 10 watts and divide it by 4 pi r squared. Oh, I'm missing a square here. It should be r squared. Don't forget. That big typo. Okay? Intensity, irradiance. That's why I'm saying it's easy to get confused with the terms, so try to just become familiarized with it. Is everyone okay with this? That's a relatively simple problem. Okay, moving on. Let's look at the next problem, which is a little more complicated. So in this case, it's a flashlight, just like this one, right? So instead of a lens, it is using a parabolic reflector. Okay. So here we have a source here. I need to get better point. This source here, okay, has radiant power of 200 watts, 200 milliwatts. Oh, that's pretty lot. So the question is, and the geometry is given there. So the 3 centimeter diameter of the source, and it forms a spot of, let's say, 10 centimeters, about 25 centimeters away. So that gives you an idea of what the divergence of the source is. Okay. What is the question is, number one, what is the irradiance at a distance 25 centimeters from the flashlight's front window? Number two is, what is its radiant intensity? So I'll let you think about this problem for about a minute. So feel free to discuss. So the first question to answer is, what is the question asking for? Right? It's asking for irradiance. So we need to know what that is first. Right? So we saw from the previous question, if you don't remember, you can just look it up. Right? From the previous question, this is asking for watts per meter squared. So we know 200 milliwatts coming up, and we're already told that 25 centimeters away, it has a spot size of 10 centimeter diameter. So all you have to do, if you make the assumption that it's an ideal optical system, the parabolic reflector is perfect, you're not, no losses. I will do is take the 200 milliwatts and divide it by the area for which it's falling. Okay? So it's pi times 10 centimeters divided by 2. Right. Right. That's my radiance. I made a big assumption, of course, that is 100% efficient. That's okay. I mean, in this class, we can make assumptions. It's simple, relatively simple. If you know what the terms mean, that's what I'm saying, that's what you need to clarify in your head. Radiant intensity. So what's radiant intensity? We know from before, This is watts per steradians. Right? So in this case, we need to know the steradian at which it's emitting. So for that, we have to do some geometry, right? So we know. So what are we trying to do? We're trying to figure out what is this cone angle, right? From that, we can figure out the steradian. So you need to know some solid geometry here. I won't work through it. So you should try to figure it out. If you can't do it, try. You can come back and ask me. But from this theta, which is this cone angle here, and you assume it is a section of a sphere, right? So once you know the theta, that theta divided by 4 pi is the fraction of the sphere, right? And you multiply that. So that's the steradian. So you divide that. So 200 milliwatts is basically going into this many steradians. So you take the 200 milliwatts, divide it by this many steradians. And get the answer. Of course, this is actually not exactly right, because you have to convert it to omega. So there's a conversion from theta to omega. Theta is the two-dimensional angle. Omega is the three-dimensional solid angle. Okay. Which I actually put some links on the website, so you can go take a look on how to do that conversion. It's not that hard. It's just geometry. Okay, but I won't go through it today in the interest of time. But that's the idea. So my advice for these sorts of problems is try to understand what the question is asking for. Once you know that, then you will know how to answer that question. Okay. Okay, so let's move on to the last topic, which is color. Color is very, very important, and there are many things in lighting where color becomes very critical. So let's talk about this briefly, and I have some examples to show you as well. So first, color, the physiological basis of color, the fact that humans perceive 3 different colors is because we have 3 types of cells in our retina. The retina is our camera sensor. Right? Our retina has actually 4 types of cells, but 3 of them used for color. Blue cones, green cones, and red cones have this sort of a response. So this is wavelength, and that's a relative response. Those cells give you that response, so blue shifted. These cells give you red, and these cells give you green. And our brain essentially puts them all together to give you the color. So it's a big neural net, right? It's going on in the cortex. Now the rods are very important because they're a different kind of cell which are not color sensitive. I mean, they are color sensitive, you can see it here, but they are in general used to give you intensity information, whether it's bright, dark. So you have color plus intensity with which you can form a picture of the scene. Just like a camera. In a camera, of course, typically you only have 3 color pixels, right? You don't necessarily have an intensity pixel, but those 3 color pixels are quantitative, so that's enough for you to form intensity from that. Okay? So the cones are for photopic vision, which is lots of light. Rods are for scotopic vision, as we saw before, low light. Now, how is color created in nature? There are many ways to do this. One is color by addition. So if you take different colors and start adding them together, you can form different things, right? So if you add up all the colors, as shown in the top row, you'll get white. And if you get rid of the green, which is what's shown here, you'll get a purple, right? So you add up everything other than the green, you get that. So you create all kinds of colors. And in older cathode ray tube displays, this is exactly what happened. You have these electron guns hitting different kinds of fluorophores which enter different colors. And by adding different colors, you get combinations of colors. That's color addition. Now, of course, in nature, I'm not familiar with anything that does this, actually. Yeah, can't think of one. There's probably is, but I don't know. Color subtraction is much more common. Okay, this is what happens in your LCD. And this is what happens in all objects. So when, well, for instance, when you perceive this chair as being red, the reason it's red is because it has absorbed blue and the green, right? White light's coming in, sits here. They absorb the blue and the green, and it's reflecting the red only to the right. It looks like it's red. Right? That's what's happening. And that's color subtraction, right? And that's what happens in an LCD. So in an LCD, the way it works, so but this is just to show the color subtraction. So you have white light from the back and your color filters here. So the blue filter is essentially absorbing the green and the red. You see blue. The red, whatever color that is. That kind of looks brown or red. But anyway, you get the picture. So this is how an LCD works, like a display on your phone, unless it's a Samsung or one of the newest iPhones, which uses OLED. It's quite different technology. The idea is simple. You come in with white light, right? Everything, if you strip the LCD down, it starts off with white light, white LEDs. And then you have some contacts which are transparent. And then you have a liquid crystal which rotates the polarization of the light. So this is a polarizer. This polarizes the light in a certain direction. The liquid crystal can rotate the polarization depending upon the voltage that's applied. If no voltage is applied, sometimes nothing happens. And then you have another polarizer out here. You have a color filter out here, which essentially absorbs the complementary color. So if you have a red color filter, that means it absorbs the blue and the green, allows only red to pass through. Okay, and then you have a polarizer there. And that polarizer is rotated 90 degrees with respect to this, which means that you can turn on and off those pixels by changing the voltage of the liquid crystal. So by rotating the polarization, you can turn on and off and do grayscale also. If you come in an angle to a polarizer, you get a fraction of the light through. But what's important for us is just the color. The fact that you have these dyes here, which absorb the complementary colors, the reason that you have a color display. Okay? In fact, if you take your phone and put it under a microscope and look at it with white light, so make your screen a big white patch, put it under a microscope and look at it, you will see this. It's big actually, you don't need a very fancy microscope, even maybe a magnifying glass you can see. But let me ask you, when you think of any other way to create color, so talk about subtraction and addition. Is there another way to create colors? And I want
it was called, but I watched the YouTube video, is about like butterfly wings.
right.
It was actually shaped a certain way that it would, I don't know, reflect only certain wavelengths or something. I don't know.
So the question is, it's a good point. The question is it absorbing the wavelengths? Then it's the same as color subtraction. Right?
Interference.
Yes, interference is the same sense, in the sense that if you're absorbing the other wavelengths, that's the same as color subtraction. But imagine
Fluorescence.
Emission.
fluorescence emission emitting. That would be considered, well, you have to put multiple of them together, but that would be additional in that case, right? Yeah. OLEDs are fluorescent. So by the way, there's a big shift happening in these display technologies, as maybe you know from the iPhone announcement. So everything is moving towards these OLEDs because of the huge color saturation on this kind of business. Yeah, and you can turn it off completely and so on. It's a big disadvantage of cities. The OLEDs are super expensive. So OLEDs are basically LEDs, right? Just like we drew before, like this. Except that now they can adjust. They can make them with organics because LEDs are still too expensive. You cannot have millions of LEDs, inorganic LEDs. But if you can do organic, if you can cheap enough, then you can do it. Then you control color with organic chemistry, essentially. Sorry, what was I going to say? Yeah, so I was going to say that what you suggested is still an addition. But you can do color in a very different way. For instance, think about the light coming here, right? This is white. All wavelengths are coming here, right? But if I had some way that I can essentially redirect the colors, not addition or subtraction, split them out, like with a prism, right? I can create color, right? It's another way to create color. So I'll give you an example. So this is an example from my lab, which is not a prism, but it kind of looks kind of like it. So you can see color. Here, it does something very specific, which we will talk about later in this class. It's actually a solar concentrator. Can you see the color here? Can you all see the color or not? Is it too small? Too small. Really? You can see it? You're welcome to come up and look at it later on. But there is color. Okay, and the way this creates color, for instance, is by redirecting the light. And there are some reasons why you may want to do it that way as opposed to absorption or addition. Because if you're doing absorption, you're losing energy, right? You're throwing away photons. So you do not want to. So I want to show you a video here from which does exactly what I just told you, but they're trying to do this for a lens, for a camera. So they're trying to make a camera. This is from Panasonic in Japan. They're trying to make a camera that will work really, really good under low light conditions. You don't want to throw out any photons. You want to throw out every single thing that comes through, but you still want to know the color. So let's take a quick look.
Taken using CCDs with the same sensitivity.
Let's start here.
Panasonic has developed a unique technology that doubles the brightness of color photography by using micro color splitters instead of conventional color filters in the image sensor. These two photos were taken using CCDs with the same sensitivity. The one on the right was taken with the color filter system used in nearly all digital cameras, and the one on the left was taken with Panasonic's new micro color splitting system. Until now, image sensors have produced color pictures by using red, green, and blue filters for each pixel. But with that system, 50 to 70% of the light is lost.
今回はカラーフィルターを用いない、その結果として光の損失なく光を取り込むという、かつ CCD とか CMOS または BSI といったいろんな種類のセンサーが提案されていますけれども、その種類によらず適用が可能な技術です。もう一つは現行の半導体プロセスを用いて適用することができます。特殊な材料を用いているわけではなく、特殊なプロセスでもありません。
This photo shows a cross-section of the new image sensor. The sensor uses two types of color splitters, red deflectors and blue deflectors. The red and blue deflectors are arranged diagonally, with one of each for every 4 pixels. RGB values can be obtained by determining the intensity of light reaching each of the 4 pixels. For example, if white light enters each pixel, pixels where it doesn't pass through a deflector receive unmodified white light. But in pixels with a red deflector, the light is split into red diffracted light and cyan non-diffracted light. And when white light passes through a blue deflector, it's split into blue diffracted light and yellow non-diffracted light. As a result, the pixel arrangement is cyan, white plus red, white plus blue, and yellow. The RGB values are then calculated using a processing technique designed specifically for mixed color signals. To design the microcolor splitters in this way, it's necessary to analyze optical phenomena such as reflection, refraction, and diffraction in 3D. Analyzing various wavelengths of light for each form of microcolor splitter requires high-speed computation, which hasn't been practical until now.
全く新しい解析手法を開発いたしました。バビア DTM と呼んでいますけれども、一般に使われている FDTD 法に比べて325倍、メモリの演算速度、メモリ消費量としてもわずか16分の1ということが分かっております。こちらは FDTD を使って3時間かけて計算した結果です。同じ結果がわずか 36.9 秒で実現できます。今回は2ディフレクターというやり方を採用しましたけれども、例えば4つのディフレクターを使うともっと SN が高くなるとか、そういったいろんな組み合わせ、それこそこの組み合わせの時には例えばモバイルに使える用途になるとか、この組み合わせだったら監視カメラに使える、そういうふうな方式と用途との組み合わせというのがそれで対応していますので、その辺の研究。
So I'll stop there. But you get the idea. So this is an example of reflecting the different colors in a very described fashion. such that you get the colors, right? Different wavelengths go to different locations, essentially. And like he's saying, the idea is that you don't lose any photons. You get better sensitivity to the camera, for instance. So in my lab, what we did is we made a solar concentrator, which we wanted not to lose photons either. We want to collect everything. So that's the reason. We'll talk about that in a few lectures. So the last topic I want to talk about is colorimetry. How do you measure color? This is just conceptual. You don't really know mathematics. But color is, of course, psychological. So this is a whole topic in itself. People have written books on it because how do you know that when I see red, is it the same as when you see red? We don't know, right? So it's all psychological unless we do some neurological studies, which I think are starting. No one's actually done it quite yet. So how do you quantify physiological color perception caused by certain spectral color stimulus? For this, of course, the reason to do this, we need some standards in order to design systems, right? We need to design lighting and so on. So you need to have a human standard. So that's the reason for this. So there's this theory called the Strice stimulus theory, which basically says that every color that can be perceived by a human being can be described by 3 numbers, X, Y, and Z, that we will see, okay? Which quantify essentially the stimulation of the red, green, and blue cones of the eye, okay? And this is standardized by this thing called the Commission Internationale de l'Éclairage. And I don't actually remember what it means, but CIE is something you will see all the time. That's the acronym for that. And the standard colorimetric observer defined XYZ color matching function. So this helps you define these 3 values, which tells you, okay, what is this color? Okay, some standard. And the matching functions are defined here. This is, by the way, done basically by doing huge statistics, surveys of lots of populations to figure out, okay, what is people's response. And it changes with age, changes with culture, and so on.
Question, couldn't you just measure it, or won't every color have its own wavelength?
Yes,
Could you
it
just say this is...
It does. The problem with that is that different colors, different spectral response. So in other words, it's not a one-to-one match. In other words, there can be 2 colors which look identical to you or me, which can have very different spectral content. So you're absolutely correct. This is how you would do in a radiometric system. But I can put 2 spectra here which look completely different, but in a plot. But if I look at them, they look identical. So they were trying to avoid this issue.
Gotcha.
So you need to have some unique way to define what a color is. So they define this color matching functions, which is basically this red, X bar, Y bar, and Z bar, each for each color, standard. The tri-stimulus value for a color with the spectral distribution I of lambda. So this is the translation from radiometric, which is spectrum, right, to X, Y, Z. So you take the I of lambda, which is our spectrum, multiplied by this function, X bar lambda, which is the red one here, for instance. And you integrate for the visible range, 380 to 780 nanometers. And you get this value excess. And you still do the same for Y and Z. Okay, so you get 3 numbers. And then you normalize them typically, and you draw these diagrams, which I'm sure you've seen before. Okay? So in tri-stimulus, we'll see about this in a second. You define color and brightness, basically chromaticity and brightness. Y, which we saw in the last slide, is a measure of the brightness or the luminance, while X and Z are measures of color or chromaticity. So then you define the small x and small y by normalizing the capital X and capital Y. Okay, and then you draw this form. So we use, and these are called projected coordinates. You take from 3D and project into 2D. XY to define color, and this is called a chromaticity diagram or a CIE diagram, which you will see all the time for any display, any source. Okay, and this is a plot of x, small y, and it's a locus here. Okay, this defines, for instance, the gamma of a display, like how many colors can a display actually display. So that LCD display here, how many colors can a display, is defined by this locus, which kind of looks kind of like this. These are the different colors, and this is what I mean, right? And you can look at any of these. These are unique colors, but you can have many different spectral responses because they've undergone that integral, right? So it's not a unique mapping from spectral The edges here of this locus are pure colors. So this is 380, that's a laser at 380. So it's a delta function. Right? And if you go along the edge there, those are delta functions of those wavelengths. And it's going around 380 all the way to 700 in this case. Okay, I think that's my last one. So that's the last thing. And we'll end here. Any questions? I can answer if you want.